Hello and welcome to Functional Programming course. My name is Dmitry Soshnikov and today we will talk about another algebraic data type, namely trees, and how to represent them in a functional programming language. You probably know what trees are. Trees are structures like that when you have node and some number of associated subnodes. And if you have any number of associated subnodes, that is called generic tree. If you can have only two subnodes, left and right subnode, it is called binary tree. And we will see different usages for different types of trees. Namely, general trees are used to represent things like directory structure in your computer. If you think about it, all files or folders are organized as a generic tree. Or any program in any programming language can also be represented as a tree, which is called abstract syntax tree. And that is very useful when you are writing compilers to represent the structure of a program. Binary trees, the most obvious use for binary tree is binary search tree, because as you know, in a functional programming language, you cannot have array, so you cannot organize binary search. But if you want to search effectively, using more effective strategy than just linear search, then you can use binary search trees. Or also binary trees are used to represent generic trees as well. So how can we define trees in a functional programming language? Well, similarly to lists, we know that a list is an element of type T and a list of type T, head and tail. For trees, we can think of a tree as the element of type T and a list of subtrees, which should translate to F# pretty much directly. So we can say that type T3 is the element of type T and the list of subtrees. However, if we try to define it like this, we will get an error. It says that type definition involves immediate cyclic reference. And that is not good because the type is defined immediately in terms of the same type. The way we can handle that, we can make it into the union, into discriminated union. We will say that tree of type T is a node which consists of an element and a list of subtrees, and that would be a correct definition of the generic tree. So that is the way that the tree can be defined in F#. It's worth noting that from mathematical point of view, a tree is an acyclic graph. So we can use also any methods we used for representing graphs, for example, the adjacency matrix. But dealing with the matrix representation of a tree is not convenient because it makes it more difficult to traverse a tree, to find immediate subnodes, and so on. Also, with the matrix representation, you need somehow to store the actual structure of a node itself. So that is not being used. That is the way we normally would represent a tree. Sometimes we can find also an alternative definition when we make an explicit difference between leaves and nodes. So in this case, in the previous case, we kind of a leaf is anything which does not contain any subtrees. So a leaf is something with an empty list of subnodes. So we can, using this definition, we can define leaf as node of X and an empty list. But sometimes, to make it more explicit that there are different types of nodes, we can differentiate between leaf and node during the type definition itself. And whichever way we use the representation of a tree, like if we want to define the tree of numbers, we can do it in this way. So we can say the tree is a node which has one element 1, which is called root element, and then it consists of the list of subnodes which starts with 2, and so on. So that representation represents this tree here in this picture. So once we have defined the tree, what we can do with it? Because tree is similar to a list, we can define similar operations to lists. So for example, we can have map operation on tree, assuming that we have defined the tree as leaf and node. We can define map in the following way. So if we have a leaf, meaning to say that we have an element, then we need to apply the function f to the value of this element. If we have subnodes, we apply a function f to the element, and we need also to apply a mapping function to each subtree. So we use list.map because we have list of subtrees, and we apply mapping function using f to each of the subtrees. And similarly, we can define the fold operation as well. We will define the fold operation on trees in terms of list fold on all of the subtrees. Those are powerful operations, and as in the case with lists, you can define many more things in terms of map and fold. For example, as an exercise, try to define recursively the function of mirroring a tree. You can do it either recursively or you can use fold and map. So mirroring a tree, meaning if you have the tree 1, 2, 3, 4, you should get the tree 1, 4, 3, 2. You can try to define the function which deletes all leaves. So it will just go and get rid of all the leaves and leave only non-leaf elements. Also try to define the function which computes number of elements in the tree. That should be very simple. And getting the height of a tree, so the number of levels the tree has. So I mentioned that map and fold operations are very similar to lists. And when we were talking about lists, we were talking also about lifting in terms of domains. So with lists, suppose we have the function which takes a string and computes the length of a string. So this function maps string domain, so string type, into int. And to this function, we can automatically construct corresponding function in the domain of lists. So for each type in our programming language, for string, we have the corresponding list type, list of string. And for int, we have the corresponding type, list of int. And automatically, by applying the map function to length, we will get the function which maps from string list to int list. So this map, what map does, map allows us to lift the function length from the domain of strings into the domain of string lists. And the same goes for trees. We can build the mapping from string to the corresponding domain of string trees and integer trees. And the mapping function would take string tree and map it into integer tree. So again, we have the correspondence using the tree map. We would be able to lift this function into the domain of trees. You see, there are a lot of similarities. Like in the functional programming, we can think of this abstraction of lifting as higher order operation, so to speak. And as we will learn later on in the category theory, it is called the functor. A functor can be applied to any type. So in this case, lists is a functor, and we can from any type we can build list of this type, and from any function between two types we can build using map operation the function in the domain of in the functor domain. And tree is another functor. From any type in the underlying programming language, we can construct the tree of this type, and from any function from one type to another, we can construct the mapping function in the tree domain. That is very important way to think about things in general, about lifting the level of abstraction of a function. And the functor can be thought of somehow more complicated structure which takes all the functions with it. So all the functions which you have in the underlying domain, we can take with us, lift them to the domain of trees. Now let's consider a specific type of tree, abstract syntax tree. And abstract syntax tree, as I mentioned, they are often used to represent programs in a programming language. But we will consider a simple case. Suppose we want to represent an arithmetic expression. So something like 1 plus 2 times 3. We want to represent that. And to represent that, of course, we can use binary trees. We can say it is the same as multiply the result of adding 1 and 2 and multiplied by 3. So we will have this kind of binary tree. But in this binary tree, the node, the value of the node would be either a number or an arithmetic operation. And we can, of course, store this arithmetic operation as the character or as integer code. But what we can also do, we can define the tree type, which would have several different nodes. So we can say that an expression of type t would be either addition or subtraction or multiplication or division. And that would be binary operations, which would consist of two possible subtrees. Or it can be a negation, which would have only one subtree. So negation, if I want to add, for example, if I want to multiply by -3, in my tree, I would have the negation node here and the tree number 3 here. Or it can be value. The leaves would be represented by value of type t. So this would be value of 1, value of 2, and value of 3. So you see, this abstract syntax tree is a kind of special case of a tree. It is not generic in a sense. I cannot have any number of subnodes. The number of subnodes depends on the operation. For example, for addition, we have just 2 subnodes. For negation, we have only 1 subnode. And for some really peculiar operations, like if we want to represent ternary conditional operator, like in F#, when we have in C++, for example, or in C#, when we have the conditional operator, if x is equals to 1, then 0, otherwise, so it's like this, then 0, otherwise 1. It would have 3 subnodes: the conditional expression, left and right sub-expressions. So the node, depending on the type of node, we will have different number of subtrees. So that abstract syntax tree can be represented really nicely in F#. It looks very similar to the original grammar of the language, right? So if you want to define this this tree, the arithmetic tree, I would say 1 plus 2 times -3. I would say it is multiplication of addition of 1 and 2, and then negation of 3. So something like this. And it's very natural to define the functions which will use this tree. So for example, if you want to compute an expression, we can say, okay, I want to define function compute. And if we want to compute the addition, we add the results of compute of left and right subtree. If we want to define the result of subtraction, we compute the x minus compute y, and so on. So that is very natural definition to process this abstract syntax tree. And if we want, for example, instead of compute, if we want to translate it into any kind of assembly language, you can imagine that would also be quite easy, because instead of recursively current compute, we will just call the function to emit the part of machine code which would correspond to this expression. So that is one of the ways to build a compiler. First of all, we need to translate from text into the abstract syntax tree, and then from abstract syntax tree, we can either compile it or interpret it similar to this compute function. Now let's think about the first part of this expression, of this process. How can we parse a text into a tree? For example, how can we parse the expression into the abstract syntax tree? Well, one of the ways to build parsers is called recursive descent parser. And definitely building parsers is the separate topic. And there are many different ways to build a parser. You can use, we will later on talk about monadic parsers. But right now we'll consider one simple way to parse a text into a tree, which is called recursive descent parsing. So the idea of recursive descent parsing is to build a set of mutually recursive functions, each of which will be responsible for its own part of the tree. So for example, if we have in the tree the negation, which should understand -3, and suppose I want to parse something like -3 plus 8. So the recursive descent parser would know that, and for simplicity, let me represent unary minus by a different symbol. So the recursive descent parser would see that this initial expression can be parsed using neg, and it would call the function neg, which will parse this part of the tree, and it will return the corresponding subtree, negation of 3, and the rest of the substring, which is plus 8. So the idea of this recursive descent parsing is that it will take the stream, and each function will take only the number of elements in that string which it needs to do parsing, and then it will return the result, the parsed tree, and it will return the remaining of the stream. And like that, it's possible to like each parsing each of the elements would be calling a corresponding function. So we will consider a simple example here. We will parse the prefix expression. Prefix expression is a way to write an expression when you have first the operation and then two operands. So suppose I want to represent 1 times 2 plus 3 in the prefix form. So it would be represented like plus, then multiply, then 1, 2, so 1 times 2, and then plus 3. So when parsed into the abstract syntax tree, it would return us something like this. Add, multiply, value 1, value 2, and then value 3. So how can we build this parser? This is, of course, a simple example because the good thing about this example is that once we see the operation, we know how much we need to parse. And but the idea would be the same. So we would have this function ff, which does all the job. So the function ff will take the list of tokens. So this is the argument that ff will take. And what it will return us, it will return it will return the tree and the remaining portion of the list that it cannot parse. So suppose I call my function ff on the list multiply 1, 2, 3. So if I call my function ff on this list, it would parse as much as it can. It can parse only multiply 1, 2. So it will return me the part of the tree, multiply 1, value 1, value 2, and it will return me the remaining portion of the list, which is 3. It will return a pair of values. So how the function ff will work? For empty list, of course, we cannot do anything. That's why we fail immediately. And then if we have digit as the first thing, and we will only deal with numbers which are digits for simplicity. So if the h is a digit, then we return this digit as a value, and the remaining portion of text is t, right? Actually, I was a little bit wrong here. We have different order. So here 3 goes first. So it will return the remaining portion and the tree. And the tree for the digit would be value of 5. So if we have, if the element is a space, we can just skip it. That is a simple way to skip white space. If the element is the unary minus, and as I mentioned, for simplicity, we use different notation for unary minus. In this case, we parse the remaining tree, t, and we return the result of parsing and negated tree. So we will add the neg operator to the parsed subtree. Then, if we have an operation like plus or minus, and this is the only this is the remaining case because we can only fall here if we have plus minus divide or multiply. In this case, we call parsing once, call parsing twice, and we return the function mknode, and mknode will construct the name of the tree. So from plus it will return add, from minus it will return sub, and so on. So it will return us the corresponding constructor, and we will construct the element of the tree. So if we have something like the original expression plus multiply 1, 2, 3, we will first call the function ff. It will call this parsing, the first parsing. The first parsing will return this sub-expression, and the second parsing will return this sub-expression. and it will unify it into the add element of a tree. So that's how this recursive descent parsing works, and that's a really useful technique to build simple parsers. Finally, the original function parse prefix just returns the second part of the ff function. So assuming that the parsing has taken place correctly, we just need to omit this remaining portion of the list and return only the sub-expression. So as an exercise, that was a simple way to build a parser. If you want to get deeper into this and practice yourself, you can try to build a parser which parses an expression in infix or postfix form. Postfix form should not be very difficult, but infix form is more complicated because you have to deal with things like brackets. For example, you can have different expressions like 1 plus 2 times 3 or 1 plus 2 times 3, and those correspond to different trees. So to parse the infix expression, you probably would need to read a little bit how this is normally done, because we distinguish between two different types, terms and factors. So factors are something which are arguments of multiplication, and one function would be building those kind of higher precedence operators like multiply and divide, and terms are responsible for building plus and minus, sums and sums essentially. Simple exercise would be to build a variable substitution. So suppose you have a tree and you also extend it by the notion of variable, not only the value but also a variable, and you can build the variable substitution. Or you can also try to experiment with computing expressions, like computing a postfix expression is the simplest thing you can do with expressions. You can do that without trees, by the way. That is a very simple thing, but think how this can be done. So this is just to think about. You don't have to write that unless you don't want to, but writing those kind of exercises will actually deepen your understanding of how expressions work. One more way to represent a tree is to use a generator. So suppose you have a directory structure inside the computer, and the directory structure in operating system can be retrieved using some system call, and system call typically gives you files in the current directory. So in .NET, because F# is a language built on top of .NET, we have this called directory.getDirectories, which will return us all subdirectories from the current directory. Not from the current, but from the given directory here. So suppose we just want to print the tree of directories starting from the current one. So what can we do? So this we want to specify a directory and say I want to print the tree. And when you print a tree, you would need to represent it graphically in a nice way. So we will also add the number of spaces that you should print in front of this, of any file name in this directory. So how can we do that? We for current directory we call get directories, and then for each directory in the result we print its name, and we also recursively print everything inside this directory as well. And this gives us the nice tree-like structure. Try to get this code and execute it and see for yourself what happens. So here we don't have an explicit representation of a tree because the tree is being built as we go, right? During the execution, we just traverse it and we process it one thing at a time. Now let's consider a little bit more realistic example. Suppose we want to build a function that will calculate the size of directories. And that is similar to the Unix command du, disk units, which will just print out the sizes for each directory in the given directory. So how can we do that? That is very similar to the previous example. We get all the directories in the current directory. And then we need to, for each of the directories, what we do, we get the files in that directory. We do array map replacing the file name with the file info structure, which contains also the size of the file. And then we do fold, and fold goes through each of the files inside the directory and adds the lengths together. So we'll compute the total size of the files in the directory and print it out. And then we do the recursive call. So if the current directory is a directory, we do the recursive call. How does this work? Let me show it to you in the Visual Studio. Here is that definition. Let's execute it. And then I will have the directory deep data with my data sets. I call it, and here you go. It started traversing all the directories and computing the sizes. So you see we have created something similar to the Unix command with just a couple of lines of F# code. So we have talked about general trees, and in the next section, let's talk about binary trees.